Thank you for the invitation to be here today. It's a pleasure. So as mentioned, I'll talk about just a bit of an overview of the ECP efforts overall, but really focus on the software aspects of things. So let's get started. So the Exascale Computing project has a mission to develop the applications, the software stack, and interact with the vendors and facilities to make sure that we have a capable exascale simulation and data science infrastructure in place in the early 2020s. ECP is part of a much broader initiative, ECI, Exascale Computing Initiative. So we're not all of the activity that's going on in the United States for exascale computing. In fact, the program offices are also heavily involved in DOE, and then the facilities themselves are collaborators with the Exascale Computing project, but they are not part of. And so, if you ask me questions about the systems, or I'll point you to the facility staff for the details on those activities. There are three primary focus areas within ECP. Applications development, we sometimes call AD, software technology, ST, and then hardware and integration, HI. I'll just mention a little bit about AD and HI and then dive into the ST efforts. So AD has 25 applications. So these are often starting points, existing applications, but they really are very significant application development efforts. And probably key in them are things to get ready for the accelerated platforms we anticipate these exascale platforms to be, but also to do fundamentally new capabilities. Most of the application teams don't want to do the same thing at higher fidelity. They would like to couple physics and couple scales. And so that's a strong theme throughout all of ECP, and it actually drives a lot of the activity in the software technologies area as well. These are the primary areas as national security, energy, economic, scientific discovery, earth systems, and healthcare, and we have significant efforts in all of these areas. I wanted to highlight the R&D activities and challenges that the apps face because they in turn are our challenges in the software technology. In a certain way, we exist to satisfy the requirements of these application teams, not just the 25, but certainly these 25, and then a broader collection of applications. So porting to accelerator-based architectures, that is the path to exascale in the time frame that we have right now. Exposing additional parallelism, coupling codes I mentioned, and I'll mention a bit about how that impacts software technology, new math approaches, and then model improvement, algorithmic improvements, and then optimizing or leveraging optimized libraries, which is what ST provides. In the HI area, we have the Path Forward projects that are going on, and also they are in a sense the glue of the project in a lot of ways. So they help us coordinate the AD applications and the software technologies area with facilities, with the vendors. And so they're very much a conduit and a coordinator of activities across ECP, a really important part of the project overall. These are the platforms. You've seen this roadmap probably before if you're paying attention. So Frontier and Aurora and El Capitan are the three systems that we're targeting for ECP. AD helps the software technology areas and the other parts, as I mentioned. They're critical to our success. In particular, we talk about in the software technology areas, we do research in algorithms and software technology. We do development of software capabilities. We do delivery of those capabilities, usually into open source repositories. And then AD, or HI, the hardware and integration folks, help us do the deployment. They help us that last mile of effort that we require in order to get onto the platforms at each of the facilities. Okay, now a bit about software technology. So these are our challenges. We are extending current technologies to exascale where possible. A really strong theme of ECP is not the brand new programming models and environments. It's really about taking as much as possible the existing capabilities we have in programming models in particular, for example, MPI, really carrying that forward as much as we can. OpenMP, and making that ready and robust for the anticipated exascale platforms. We're doing as much of that work as we possibly can. We are certainly doing new R&D, new approaches where necessary, And then we're doing this efforts with the vendors and with the facilities so that because we're a part of this bigger ecosystem that everyone participates in. And then also within ECP, software technologies, we have an emphasis on software quality. We believe that there's an opportunity with mainstream industries, other software domains to learn from and leverage software practices that are going on in these other communities, and we can bring those in, adapt them, and adopt them into our own teams. The bottom line is we're doing roughly 90 open source scientific software products, bringing those forward to what we anticipate exascale platforms will need. We're doing software development kits, which I'll talk about in a bit. It's one of our, I think, a fairly innovative approach to providing composites of existing software products and making them easier to use, more interoperable. And we're providing what we call the Extreme Scale Scientific Software Stack, E4S, which is the entire aggregation. It's the kitchen sink, if you will, of the HPC software stack that we're trying to provide. And we're really quite excited about that initiative within ECP. All right, so these are some of the entities I already mentioned, our collaborators, the apps, the facilities, the vendors, and then the broader HPC community. We're very interested, especially within ST, because we're about reusable software, in engaging with other agencies within the US government, NASA, NOAA, NSF. In fact, we're hosting, or NSF is hosting a joint workshop with us this summer to leverage and build an understanding and ability to use what we're providing in software technologies, especially the E4S activities. And then also internationally, we're very open to collaboration. In fact, many of the efforts within the software technology area, the MPI developments, MPI-CH, OpenMPI, OpenMP, these are truly international collaborations. And so we want to foster that, and we want to recognize that we need to be international in our activities. So the orange boxes are the four primary technology areas: programming models and runtimes, development tools, math libraries, and data and viz. And then we have a fifth area, software ecosystem and delivery, which is really quite unique because it's totally focused on getting stuff out the door. And that's what it's about. So in that area, you'll find the efforts in the SDKs. You'll find we're just starting a brand new effort in FY20 in container technology. We're very enamored of containers. SPAC, and I'll talk a bit about those things in a bit. Oops. Okay, so what do we work on? Well, there are a lot of words here, but let me just focus on a few things. Things that you know. We work on MPI, both versions, OpenMPI and MPI-CH. We work on OpenMP, OpenACC. A lot of that is actually done through LLVM. We have a strong LLVM-centric set of activities. Performance portability layers, things like Cocos and Raja, are heavily funded within ECP. Performance tools, you may know a few of these: PAPI, Tau, HPC Toolkit, math libraries, certainly the BLAS, LAPACK, and their next generations, but also sparse solvers, PETSI, Trilinos, and so on. And then in the I/O area, again, names that you recognize. And then in the viz and data, certainly, for example, ParaView and related activities. And carrying all of these products forward to the accelerated platforms that ECP has to target. Again, these are the areas. I've mentioned just a few things. For example, the Solve project, the LLV in Solve is for LLVM. This is an effort that's focused on getting the key things that we need for high performance into the LLVM stack, upstreamed into the base repositories of LLVM. PAPI, the performance API, is another example. StrumPack is a new sparse direct solver package, which is a critical kernel for many applications. It's based on some really exciting technology that's emerged in the past 5 years that look at low-rank approximations to do sparse solves. And they're turning out to be really effective, even for real three-dimensional problems. Sparse solvers had always been relegated to 1, 2, and 2.5D shell-type problems. StrumPack has the opportunity, the potential to impact 3D problems. Data compression, another very interesting technology. We have two projects, ZFP and SC, that focus on data compression, which allow you to get IEEE resolution, but at a much lower cost in terms of storage. And some nice classes built around that, so you can use arrays that store data in the ZFP compressed mode. And then, of course, SPAC, which we use as a meta build tool that sits on top of the build tools that all of the builds for each of the products that we provide. Another really important part of our activities are participating in forums. The best software, the best interface that we can write is the one that we share with other people. And so being engaged in the standards committees, MPI, OpenMP, BLAS, C++ are really important for us. And we play a critical role. Certainly other people do too. But for example, in the C++ standards committee, we are one of the people who care a lot about high performance. We care a lot about not having lots of data copies laying around. We care about unmanaged data, living on the dangerous side of things. And so we put these things in. We want this stuff in the standards. And so we go to these meetings and we make sure that our concerns and your concerns are represented in this. So as I mentioned, these are some of the products. I'm not going to go through them in a lot of detail. I'll give you some pointers at the end of the talk for where you can get more information. Software development kits. So one of the things, this started about 5-6 years ago in the math libraries area. We recognize that there are a lot of math libraries. They can interact with each other. They can be used in a lot of products. And we also saw this multi-phase, multi-scale, multi-physics phenomenon where people were bringing codes together. And so now all of a sudden, if you had one application using one library, say PETSI, another using Trilinos, you had to pull them together into a single executable. That was actually really hard to do. There were things like unmanaged header files that had different struct sizes, and so you wouldn't know until you ran the code and it core dumped that you had incorrect code. And so we had to focus on bringing these libraries together and making them self-consistent, and then also making it possible so that if you were using data structures from one library, you could then still use the solvers packages from another. And so that started this whole notion of having SDKs. And what we've been able to do is bring libraries together, and this is now expanding to other parts of the software stack that make it a turnkey ability for users to bring in any selection of these libraries together and know that it will work. That they won't run into these anomalies that they've been used to in the past. It doesn't totally eliminate the complexity of using lots of third-party software, but it strongly reduces it and allows us to work together in a much more effective way. And so we've been applying these principles now to the math libraries and extending them into the other areas. And so these software development kits. And another really important aspect of this is the development of community policies. These are statements of how will we support our users. And that allows our users to have more of a common look and feel, common interaction model with us. It forces us to raise our game in how we provide support to our users, and also it helps us in best practices. And coming up with these policies is often a heated discussion. About what is the best way to support users in reusable software, and leads to a deeper understanding and more common understanding of how to best support our user base. One of the key things about the SDKs is this notion that if we have a common substrate, we can manage that explicitly. I'll use the example of PETSI and Trilinos again. Both PETSI and Trilinos use this SuperLU, a sparse solver package, but we didn't coordinate on which version of SuperLU we used. And so if somebody wanted to use both PETSI and Trilinos in an application, they had this problem underneath that one version of SuperLU was being used by PETSI, another was being used by Trilinos, and so they couldn't reconcile that without our assistance. One of the SDK promises is that we make those things consistent as we go forward. This is something about the community policies in terms of what we provide, and I won't go into a lot of detail, but these policies are very useful for us and for our community as well. I'm not going to go into this in detail, but what I want you to look at is the number of green bubbles in this, because this is 2017, December 2017. We had already been at the XSDK effort. This is the Math Libraries SDK. And the green ones are the math libraries that are part of it, or compatible with what we've been doing. And then between December 27 and December 2018, we were able to grow the number of available libraries in this XSDK model very substantially. And now, that doesn't mean they're all monolithically developed. That's not at all what we're doing. Each of these teams is still working independently, but what they've done is they signed up for a certain set of policies, an interaction model that allows users to much more easily get access to all the libraries. And this is the model that we're putting forward with these SDKs. This is this planned set of SDKs. So again, this effort, a lot of effort went into grouping these products. There are 6 of them altogether. The far right one is an at-large thing with things that don't really quite fit in an SDK. But we have the math libraries, programming models and runtimes, core, tools and tech, compilers and support, viz and analysis, and then data management and I/O. So what we're doing now is we're doing the same kind of thing that we've done with the math libraries to these other areas. One of the most exciting initiatives for me, at least, is that because we now have in the data management area all of these products sitting under one umbrella, is we're talking about making the major I/O libraries available underneath the HDF5 API. So that is the most common API in our applications, at least, for getting access to I/O services. And so we're asking all of the other I/O libraries to write an adapter for the HDF5 API so that you can use these other I/O libraries through the same interface without disruption in the application. Okay, so that's a bit of a summary. I think I've said pretty much everything. So in a certain way, the SDKs are an internal organization property. If you care about reusable software, you might care about what we're doing in the SDKs, but they're really an internal organizational effort for us. What we really care more about from an out-user perspective is this E4S effort. So E4S.io, you can go out to the website if you want, is our initiative to bring together all of the software that we are developing and all of the supporting substrate using SPAC as the build tool to regularly compile and test on, first of all, on more vanilla Linux clusters, but increasingly on the leadership platforms so that we can do continuous integration testing in these environments. We have a very nice architecture for doing this. We have a centralized GitLab reflector that pulls from the native repositories of the teams and then provides the reflected clones out to the runners that are actually doing the integration testing at various platforms. So it's a quite scalable model. And then in addition to the from source build that we use the SPAC for, we also provide 4 containerized versions. So Docker, Shifter, Singularity, and Charlie Cloud. And this is a very useful service for people. For example, at the ECP annual meeting that we had in January, the Candle project, the Cancer Deep Learning Environment project, was able to use our Docker image to do their tutorials. So they didn't have to create a stack. They could just grab this image, launch the container, and then put their layer on top of it. And we foresee this kind of turnkey software, bring your own software stack as a very attractive part of what we're doing. And so we're increasing now the number of software technology products that are available through E4S. What you have to do to become part of that is to be able to build with SPAC. SPAC is a meta tool, where you still can use your own CMake, your AutoConf underneath, but then you provide a recipe to SPAC for how to build using your build environment. These are some of the things that are in our 0.2 release. You're not expected to see that list there, but this is a printout then from the screen of that. But these are the kinds of tools that are in there, and this list will continue to grow in terms of what we provide. I mentioned SPAC a few times. SPAC is this meta build tool. It has gained a lot of popularity now within the HPC community. As a way to build software from source. And there are a lot of new features going into SPAC. SPAC stacks, if you will, is a layering type of effort, support for testing, and a registry system. And so the SPAC effort is growing substantially. ECP, starting again in FY20, will very explicitly provide additional support. We've already provided quite a bit, but increasing our support for SPAC as we see it a really important part of our ecosystem. All right, if you want to know a lot more detail, we have a capability assessment report we update every 6 months for software technology. It starts at a very high level of saying what we're about, but then the majority of the document itself is actually dedicated to a couple-page, highly technical description of each of the projects that are funded under ECP, and you can get a lot of information about what we're doing in this report. Okay, so what are some interactions that might be particularly suited to industry? Well, certainly leveraging features in our programming models. We're doing a lot of new work in MPI-CH and OpenMPI that are targeted towards accelerated platforms. If you care about getting access to the latest or understanding what is being done so you can do your own design work better of your applications, that's some way for us to interact with you. Certainly C++ compile time polymorphisms, Cocos and Raja are two library-based approaches that provide you with compile time polymorphisms so that you have a backend that it gets compiled to, and you can write fairly generic things like parallel for, reduce, scan, operations, and can get quite good performance from that without having to write a special version of that for CUDA or for OpenMP or whatever the backend ends up being. Development tools, certainly in the PapiTau HPC toolkit, a lot of effort is going into instrument and try to understand and get performance information from the next generation of devices. In the math libraries, certainly the major libraries, HyperPetsy, SuperLU, and Trillios, we've all made tremendous investments in accelerated operations so that we can now execute and provide you with solvers running on things like GPUs, for example. And then the new ones I mentioned already, StrumPack. In Data and Viz, a lot of new capabilities, especially around non-volatile memory parts, in situ capabilities, and so there's a lot of effort going on. And then VTKM, which is the node level support for a lot of these efforts, is being ported and optimized for the accelerated platforms. And then in the software ecosystem area, scalable checkpoint restart, quite a few efforts there, and then SPAC and the SDKs. Okay, what are some models for interaction? Well, first of all, you can read our papers, right? That's fine. It's a pretty weak collaboration, but it does work and can provide some information. You can go to our tutorials and webinars. We put on HPC best practices seminars once a month, and they're widely attended. We have hundreds of people who sign up and then even hundreds more that watch them later. So you can certainly do that. Participate with us, come to the meetings with us and pitch the story of HPC, because that's a really important story to tell and not everybody cares about it. And then evaluating, we're working through our ECP Industry Council members right now to do some tire kicking of our capabilities. And we consider that to be a really important way to engage our industrial partners. And adopt and rely on as an option. If nothing else, you can go grab one of our containers, right? Very low cost way of trying out the things that we provide. And then our software engineering practices, here's where we actually look to you, right? Because we are trying, we're doing our best, but we have not historically been rewarded for being good software engineers, okay? We do it anyway, we try, but I think there's more that we can learn from you, and through the exchange, hopefully we can learn from each other about what are some of the best ways to do technical, scientific engineering software, and we'd love to engage with the community on that. And then just overall, we enjoy these two-way interactions, and that's part of why I'm here. I want to meet more of you, and I've already had some fascinating conversations so far. All right, so this is wrapping up here. So we're on track to deliver this exascale computing ecosystem with our 25 apps, our software stack, and our hardware and integration efforts. We're very pleased with our efforts so far. It's a very challenging environment to be part of, as I'm sure you can imagine, but it's exhilarating as well. We just love doing this work. Here's some of the faces on the project. Doug Cothey, I think some of you have seen before in this setting. Lori Dyson is a great addition, just joining us recently as a deputy director. Andrew Siegel and Eric Drager in the application development. Myself and Jonathan Carter are the software technology leads, and then Terry Quinn and Susan Coughlin are the HI leads. And you can contact any of us at any time if you have interest, and go to this website. And then if you want to get push information, certainly go to the exascaleproject.org website, and you can just type in your email address, and we will push information out to you on a period, not high volume, on a periodic basis. So, and I think that's it. Thanks for your time.
Great pitch, thank you.
Yeah.
What does governance look like for you? So I was looking at your stakeholders. They seem to be the National Labs, Department of Energy types. How do you, is there a forcing function to get people to come play, or are you looking to accrete the software SDKs that you're seeing and produce, roll your own product? Yeah,
that's a great question. So our stakeholders are DOE and Office of Project Management, Barb Helland in the Oscar office, and Tuk Huang in NNSA. And they care a lot about what we do, and they have the funds. And what we basically do everything to make sure that we are on track with what they want from the project overall. And that provides us with strong direction, also a lot of leverage. I would argue that one of the great values of ECP as an umbrella project is it's forcing collaboration across all the labs and the associated universities in a way that we've never seen before, which I think overall is very positive, because we're seeing these collaborations being built across groups that used to compete with each other, and now it's more co-opetition, right? It's competing still, but there's a lot of cooperation, and I think the country benefits from that, the community overall benefits from that. It's a really positive thing.
One follow-up. So
sure.
Is there also international outreach that's tied to that, or is it U.S. mostly?
So officially it's U.S., but we work shoulder to shoulder with people from all over the planet. And that is the nature of enabling tech, especially in the software technology area, but also in some of the applications area. You know, when we go to a meeting for the C++ Standards Committee or the MPI Forum, that's an international group, and we collaborate with those people at a very deep technical level. So it is international as well as national. Yeah.
Hi. Have you documented operating system dependencies? And secondly, how are you handling GPU optimization as part of the programming model?
So I'm not sure what you mean by the first question. Can you say it one more time? Operating system dependencies. What do you? Just be sure I understand what you mean by that.
Yeah, any fundamental services that the OS will provide.
Oh yeah, our needs are not unusual in the bigger context of what the leadership computing facilities provide, or what you might find on an HPC cluster. And so we don't spend a lot of time worrying about that. Maybe we'll be blindsided by a small thing, but I don't see it as being an issue. And then what was your second question again? Oh yeah, GPUs. So yes, we care a lot about GPUs. Accelerators, broadly speaking, are the way to path to exascale for us. We have some people who write directly, for example, in CUDA to support Summit and Sierra. Those are two NVIDIA platforms. But a lot of our work is we're trying to make use of OpenMP. First of all, OpenMP 4.5 now supports credibly GPUs. OpenMP 5 even more. And then we also have these Raja and Cocos layers, which allow you to write more generic expressions in C++ and then have those be compiled down to, say, a CUDA environment or an OpenMP environment or something else that's coming along in the future.